Alright, so here we are in Minecraft to further explain logic gates and how they work. So first I'd like to go over just simple, very basic binary. So as you hopefully probably know, if not, you're about to know, binary is 1 and 0. 0 means it's off. This is a bit, 1 bit, which is just whatever. This is a bit. This could be a bit. Yeah, either of these could be bits. Bit is just a device that can represent 1 or 0. When it is off, when the bit is off, it represents the number 0. When you turn the bit on, it represents the number 1. There's two ways it can be. It can either be 0 or it can be 1. So just knowing that, we can go over here to AND gates. As you can see, AND gate. So AND gates, you want to get an output, or maybe you don't want to get an output, but for this we're trying to turn this lamp on. And in order to turn this lamp on, we have to fulfill the requirements of the logic gate. In simple terms, a logic gate is a gate, it's a stopping point that will not fulfill a requirement until input requirements are met. It won't fulfill an output unless the requirements are met. So for an AND gate, and I kind of like to think about logic gates as if they're if-then statements. So if, for the AND gate, if input 1 and input 2 are turned on, if input 1 and input 2 have both been turned on and they're both at the value of 1, then the output will then become 1. So if 1 and 2 are on, then output will be on. Only if. That's how AND gates work. As you can see, the second I turn, if one of them's off, then the output is still off. Only when they're both turned on, it's on. So that's an AND gate. And let's go over here to an OR gate. And just like the name says, if one or the other, or both, if one, the other, or both inputs are turned on or have the value of 1, so they're both turned on, but we could turn this one off, but this one's still on. As long as there's one of them on, then we get an output of 1. So this is 1, this input is valued at 1. This input is off, it has a value of 0. This output is then 1. You can have this is 1, this is 1, this is still 1. Only when they're both off does the output become 0. Alright, so before we get on to inverse properties of logic gates, let's first go over here. Very simple design. As we went over before, the NOT gate, otherwise you could call it the inverse gate, because that's what it does. It inverses the input. So right now the input is turned off. It has a value of 0, but the output has a value of the output has a value of 1. So it's the opposite of the input. And if you turn the input on, the output then turns off. All this does is reverses things. It flips them. So on and offs are reversed. So this inverse gate can be used to tell us false. What's false? So these tell us what's true. When these are on, then boom, true. It's a true statement. It exists. This is a 1. It's not a 0. It's a 1. So let's go over here. So this is the OR gate. This is now the NOR gate. And as you can see, they look pretty similar. So over here we first have this is an OR gate, right? This is just an OR gate, and it goes into a NOT gate or an inverse gate. So as you can see, opposed to the OR gate, the NOR gate is turned on normally. When nothing is flowing through it, and when the inputs are both off, then the output is on. It's the opposite of a OR gate. And the way I like to think about it, with the N, it's not an OR gate. A NOR gate is not an OR gate. It's the opposite of it. So just like an OR gate, the second I turn on one of the inputs, the output then becomes 0. I can also turn on the other one. They can both be on. The output will be 0. I can turn this other one off. The output's still 0. Only when both of the inputs are off does the output turn on. So when both of these are 0, this is 1. So next, let's look at the NAND gate, which is it's not an AND gate. It's the opposite of an AND gate. So just like the NOR gate, it's turned off. By default, the NAND gate is turned. What did I just say? By default, the NAND gate is turned on. Nothing is running through the inputs, but the output is on, unlike the AND gate over here, which the output is normally off. So when you turn on both inputs, only when you turn on both inputs, you fulfill the requirement to turn this off. So only when input 1 is equal to 1 and input 2 has a value of 1, when they both have values of 1, then the output has a value of 0. But if either one of them is turned off, then you get an output again. The output is equal to 1. Turn them both off, it's still on. Output is equal to 1. So that is a NAND gate. So these are 4 of the most basic gates you can make. The most basic logic gates you can make, and you can build a fully functioning computer out of these, except it'd be quite a large chunky computer. It'd be very inefficient. So, but right now I'm just showing you how they can turn on lights. You know, turning off and on lights. That's cool and all, but it's very basic. So I want to show you a more practical application of these same logic gates. So in order to do that, we're going to come over here, and I actually built a calculator. So it's an addition calculator. Over here we have a keypad, 1, 2, 3, 4, 5, 6, 7, 8, 9, just like a normal keypad. We have an addition button over here, a reset switch is here, and these are the answers we can get. So at first glance, you'll notice that you don't see any of these things. You don't see any of these logic gates in here, but they actually are. Most of this is just logic gates. So over here we have a binary converter. How it works, you don't really need to know. All you need to know is that this grid is just a larger version of an AND gate. When these requirements are met, you get an output. The output's seen over here in these pink things, but so far we haven't put anything in. So let's put in a question just to show how this works. So let's say I don't know, 4. Let's do 4 plus 6. I mean, it doesn't really matter what we put in. So 4 plus 6 is equal to 10. So the calculator is actually going to turn off the light of this value, the number 10. All the other ones are turned on besides number 10, and therefore we know it's the answer. And this will work for any single-digit addition. But so now we have values. So these have been turned on. These turn off after I press the button, and they get stored in here, these pink things. So like I said before, these are AND gates, just like over there. It's just a larger version of it. And these is just a more complicated version of the NOR gate. These are called NOR latches. And what they do, it's just like a NOR gate. When one or the other requirement is met, then they turn on. So the requirements that are being met is the numbers being pressed. So what we did was we did 4 plus 6. And just very quick rundown of how this works is we're adding in bits. We're adding in bits, and bits are different than they're different than numerical values. It goes by 2. So 1, 2, 4, and 8. Every time you multiply by 2. So 1, 2, 4, and 8. So it's the same thing. And just a really quick rundown. So we did 4. So this is bit 4. But then we added it to 6. 6 isn't an option. It's not 1, 2, 4, 8. 6 is different. So in order to get 6, we have to do 4. This is bit 4. plus bit 2. So that's just how it works, because calculators don't function in numerical values. They have to be ran in bits. These are bit adders. They add bits. So what I did is, this is bit 1, this is bit 2, this is bit 4, this is bit 8, and this is bit 16, which isn't listed here because 16 is not 1 through 9. But if you add numbers, they can be over 16. So we have this. Quick water break. Yeah, this is the third take. I haven't been drinking water, man. Mouth's getting dry, man. Okay. So, as we just went over, these are AND gates that go into NOR gates, just more complicated versions, which then get added. These aren't logic gates. They just do true or false calculations in order to... They just do math. They're not logic gates. And then these are our answers. And for our answers, this yellow part is just the opposite of this. So this converts numerical values into binary through AND gates. And if that's the opposite, what kind of logic gate should we be using? If these are AND gates and we want to find the opposite of these gates, what do we use? We use NAND gates. Remember NAND gates, when both the requirements are met, the output turns off, which is why the answer 10 is turned off, because it's the opposite. If we use AND gates here, we now have to use NAND gates here in order to put the numbers into numerical values. It's the opposite of that, because we don't want answers in binary, because that will require us to do math anyways. And we don't want to have a calculator that tells us more math to do. So for all of these, all it is these are the values. These are the values. This is bit 8, and this is bit number 2. So 2 and 8 are going to make 10, because the answer is 10. So each one of these has a separate set of bit combinations: 2, 1, 4, 1, 2, 1, 3, stuff like that. But this one over here just has 1, and the 1 has been turned off, and that means the requirement has been met. The requirement that we set, that the calculator made over here, has been met, and it was found in the number 10, because 10 is 8 plus 2, so that's why it's turned off. 8 plus 2. What am I saying? 8 plus 2. These are turned off. Therefore, this one right here is turned off, because it's fulfilled the requirements that we set. And that's pretty much it. That's just a practical application of how logic gates can be used in a more complicated kind of form. They don't have to be just used to turn on lights. They can be used to do math. And right here, the reset switch is actually just a buffer gate. I press the button, resets everything. The memory's been reset. And then here's another buffer gate right here, just in a button form, very compact. It resets the numbers. So everything's reset, and the calculator can go back to doing math. So yeah, just to review, just a quick review. This is on is 1, off is 0. Inverse gates reverse things. Whatever the input is, the output's the opposite. AND gates mean when this and this are fulfilled, then you get an output. OR gates, when this or this is fulfilled, then you get an output. NOR gates, when this or this is fulfilled, then you do not get an output. And NAND gates, when this and this are fulfilled, you do not get an output. So very basic logic gates can be used in very more complex equations, very more complex mechanisms such as calculators. You can also use these same 4 with modification, of course, like what I did here, but you can use these same principles and concepts to build a fully functioning computer. Of course, I don't have that kind of free time on my hands, but I did have enough time to build this calculator just to show how you can use logic gates in a more complicated way, that they can be used in practical applications like calculators. So that's about it. Thank you for listening to this video tutorial, and goodbye.